Today we have Andreas Wieser talking about local global principles and effective rates of equidistribution for Semisimple.
Thank you very much. It's an absolute pleasure to be here. It's also very nice to speak about this topic. I'm working very hard on it. So all of this is joint work with Manfred Einsiedler, Elon Lindenstrauss, and Amir Mohammadi. The talk will basically consist of two parts. We'll first talk about applications to quadratic forms. Applications of what? Applications of equidistribution results for semisimple periods. Okay. So applications, right? So we consider first the following. So I have two quadratic forms, small q and big Q. Okay. Those are quadratic forms. Over the integers. Okay. In also fixed number of variables k and n. Okay. And I would like to find the representation of this small quadratic form by the way. What does it mean? So, yeah, on the find. If possible, of course. That is, so it's a linear map, okay? A to the n, so that the quadratic form in the image, okay, is exactly, well, the restriction of the quadratic form to the image is exactly the quadratic form. That's all. Different way of saying that. Right? So for instance, okay, first case you should think is you take little k to be b1, then all you're looking for, because you know exactly what quadratic forms in one variable look like, is representations of some integer by your quadratic form bq, right? That's for k equals 1. If you take k bigger than 1, basically what you're looking for is a bunch of vectors, okay, where say very vaguely put, the lengths and the angles are predefined by this quadratic form here, right? Okay. For me, I will, so of course, let's over Z I have local representations in very much the same way, right? From Zp to the k to Zp to the n over R. And okay, and there's obvious obstructions. If I cannot find local representations, then I certainly can find the global representation over Z, right? That's the local global principle in this setting. Just asks if, say, suppose little q, right, is locally represented by big Q. Locally represented meaning it's representable over Zp for every p and over R, okay? Is Q represented by Q? Okay. Of course, as phrased, it's not. It's still very vague, and it's not exactly true. You should think of this as a version of the Minkowski principle. Okay, for integers instead of rationals, right? Minkowski would exactly say that if you had a quadratic form of Q, okay, and you could find a representation of QP for every P and over R, then you would find the representation over of Q, right? This is an integer version of that. Okay. So, okay. For me, so for today's talk, because the most interesting case, we'll always assume PQ positive definite. Yeah. Otherwise, use strong approximation, spin loops, makes it less exciting. So, okay, so Q will be positive. Good. So, what can we say? There is a result. So, this type of question for positive definite forms is actually people have been interested in it for a very long time. Here's a result from the 70s. It's due to Sia, Vitobra, Nixon. In 78 or so. They show that if I have sufficiently large codimension, okay, meaning if n was the number of variables of the bigger quadratic form, is at least twice the number of variables of the small quadratic form plus 3, then n, okay, of course, within Q is not fully represented, and the minimum within Q, yeah, sufficiently large, then this Q is fully represented, okay? The proof is basically a purely arithmetic methods. And well, okay. After that, it was somewhat so there's a bunch of works, this is just one of them, and it was kind of unclear for a very long time whether or not this would be the optimal condition. Okay? Which it isn't, it turns out. Here's a theorem. This is Ellenberg and Venkatesh. Yeah, published papers from 08, which basically push this codimension way down to from well, codimension here is what, k plus 3, from k plus 3 to 5. Okay, so let me just phrase it. So if n minus k plus 5, okay. And then same words. Okay, so Q locally represented. The minimum sufficiently large. Then Q is represented. Assuming for that, okay. Assuming that the quadratic discriminant obviously Q is squared. And so the methods in that theorem have, well, are really relying on homogeneous dynamics, more specifically maybe on results of Moses-Shaw type, where you're basically trying to classify measures invariant. Well, we're using statements on sequences of measures invariant, and in this case, semisimple. Okay? And we'll phrase this more precisely later. But yeah.
What happens in the indefinite case? What happens if you're not positive?
If you're now positive definite, yes. If you're now positive definite, then basically you can push this down to 3. Okay. There is a reason for this 5 here. In fact, the theorem is a bit finer than what I wrote. Is that if in codimensions 3 and 4, you could assume some type of linear splitting conditions and push and then have a similar theorem. Okay.
So it's easier in the non-positive definite case.
Yes.
Okay.
Yes. This is just me focusing on the case that I find more interesting. Good. So in codimensions 3 and 4 is what we're interested in today. Okay? Okay. Unfortunately, apparently I'm not allowed to use the boards on the side, so let's really things.
Why are you not allowed to use the boards on the side?
Because of the recording, apparently. Yeah.
Which is the new constraint?
Yeah. I'm sure it was slow. So basically, yeah. So what's stopping you from achieving codimension 3 and 4 here is basically effectivity in the method. Okay, and effectivity in the method is really what this talk is about. Okay, here's the method. Similar assumptions, okay, except for now codimension in these 3. It was represented. And there's also something different, so let me write it. The minimum of lib Q is at least some constant times the discriminant bit Q somehow. Okay. Getting something, yeah, discriminant square free. Here maybe. Okay, so now I have all the words. Locally representable, I'm assuming that the discriminant is square free and the minimum is sufficiently large. I didn't specify it before, but certainly for the local global principle for positive definite forms, it's necessary that the minimum be sufficiently large. This lower bound here is very far from optimal. It's a lower bound. Okay, so locally representable, all of that, then same statement. Okay, and Q is represented. In Q represented. Let's see. Good. In fact, it's quite a bit finer than what I'm writing here. This is just illustration, essentially.
So you also get a asymptotic for the number of representations with an error?
Yes. Yeah.
A power saving kind of error.
Yeah, basically, yes. You would want to compare the number of representation of little q or big Q with whatever you get out of sigma mass. And so the number of representation here will be 1 plus little of something like power saving, like you said, in the minimum. Yeah, compared to what you have from sigma mass. Yeah, square free is not really. It is for me at least. It's illustrate to make things a bit easier to present. Truthfully, this is all what you're proving here is a local global principle for representations of for primitive representations of factors. This is just me avoiding having to say what primitive means. Good. Okay. So I want to explain what goes into this theorem. In particular, I want to explain other words of the title that I now erase. Is a vector distribution is also Semisimple. Before I do that, maybe let me for general comment. What happens over R? Didn't have a part one, but maybe this is part two. So what do? Let me illustrate what happens. So I have a homogeneous space. Okay. In this case, it's U gamma, okay, where G here would be E group or G group, and gamma will be a lattice. Okay. Lattice is okay. Discrete subgroup, right? Discrete subgroup will find that cobalt. Okay. So you can pick most homogeneous dynamics take space copy S and the normal less than Z. That's perfectly good. Okay. Good. And in that homogeneous space, I would like to look at the sequence of orbits. Okay. Write them as xi, hi. Okay. Sequence of orbits where I'm allowing myself to change the group. Okay. And so, of course, I need something about the group. So for me, the HIs would be semisimple subgroups. Okay. No compact factors. And the orbits are periodic. So orbits are periodic means that basically, yeah. So for me, it would mean that the invariant measure, okay, the HI is finite, or put differently, that stabilizer of this point in HI is a lattice as well. Okay. Okay. So that's what I have. All right. And the type of question we're interested in this, so what's going to be, it's going to come to be an ineffective result, is just what the limiting behavior is of these sequences of periodic orbits. Okay. So there's a very nice result of Shachar Moses in Shah from 95, I think. That says the following, okay? And if you just take, so that's my notation for the invariant measure.
I think her name should also be mentioned.
Yeah, well, yes, of course. So yeah, I agree. So this is, maybe let me write it here, so I'm using that brochure. There's measure classification. And I mean linearization also, right? And the linearization technique of Tani-Makulis. Sorry, I tried to compact things so much. I think what Moses and Shaw do is classify limits of these measures. Okay, so what you should think of is somehow you have a sequence of orbits, and the orbits are getting somehow wilder and wilder in space, right? And I would like, in this case, I would like to say that the limiting orbit, in some sense, that the limiting object that I see is also an orbit, but of a logic. Okay, that's very the statement. So, but this any limit of these measures is either, in fact, I'm using also one letter, is either 0 or homogeneous, or homogeneous. Okay, homogeneous means once more basically what we already wrote, invariant measure on the periodic. Okay. Basic question we're asking is if we can provide rates in this theorem most each other. So I have some, right? So what you should think of is I have some very complicated orbit, okay? And I would like to say that it approximates some larger orbit very well. If you want to, you could illustrate what this means. So this is an illustration. What this means on the free torus. Okay. You should think of having, so in the free torus, the analogous object for me here will be a rational line. Okay, that's just a periodic line that lines around. And it can be very complicated, of course. Okay. But if you're trying to understand what exactly we said we wanted an effective version of this, right? So I should explain somehow what the rate is that I'm supposed to use. Okay. And onto this net example. So what could happen, right? I have a rational line. A rational line is contained in many rational subspaces. Okay. And while the rational line could be very complicated itself, it's possible that there is a rational subspace that is contained that is not very complicated. Okay. So the theorem, if you just very easy exercise in Fourier series, is that you can show that the rational line would approximate the back measure on the torus, okay, with a rate that is polynomial in the minimum co-volume of a rational subspace is contained. Okay, as an exercise. Of course, this is not the case we're interested in. We're interested in what we had up there. So, okay. There are theorems of this type for real homogeneous spaces. We'll get to those later. I just want to go somehow from here onwards on the geodesy to the theorem. Okay. So maybe let me switch to that. The adelic setup. Just tell you what the actual objects are. Okay. So I have two groups, right? Basically the ambient group and the small group that I want to be one. G will be my large group. Okay. That's me will be a semisimple. Be connected. Group. For all intents and purposes, for the theorem we had up here, G would be the spin group of some quadratic form. Okay, So almost you're just a special family group, but I need to simply connect it. Just for technical reasons. Doesn't be necessary. Good, so I have G. And I'm embedding G in some way. Into some SLN. Well, I'm an exact embedding, but I'm allowing myself to define that kernel. Okay. So you should think of this as being the ending group in some sense, and then there is another group, okay? H, also semi-simply connected. U. H sits in some way inside G. Okay. Okay, so that's one. I have two groups. Basically, if you forget about those technical things, H is sitting inside G, is sitting inside some SL. Okay. Good. Good. So I was promising you orbits, so let me write orbits. So the ambient space, X, an analogy to what we had up there, okay, it's going to be, well, almost the adelic quotient means, okay. You could write it maybe if you're brave, write it like this. More explicitly, I understand the following way. First, I have SLN Q. Okay, I'm thinking this is the identity quotient of SLN. Yeah, inside that too. I'm going to write something here in a second. So SLN, the identity quotient of SLN. Okay, and inside the identity quotient of SLN, I give you an orbit. The orbit serves as my ambient space. Okay. Okay. So that's my ambient space, and inside the ambient space that I'm thinking of, right? I'm thinking of this space as being the non-1, and inside the ambient space, I have basically an orbit corresponding to H. Only that I'm around myself a little more frequent than that. This is a shift, okay? So now there's a bunch of brackets that you can carry around. Just to clarify, all I'm doing is I'm taking H orbit, okay, inside X, and I'm allowing myself some shift here, okay? Not be crazy. Okay. And so there's some hope, right? That if H is very complicated compared to G, right? Let's say, for instance, if the Lie algebra of H has very large height or something like that, that its behavior inside the G orbit is wilder and wilder, and in particular, it might approximate G itself. Okay, if I'm lucky, if I'm unlucky, I erased it. There is some intermediate object that I might be afraid of. Okay. So let's write the theorem. same offers. Here's the statement. There exists some constant. Okay. The constant depends on nothing, basically. Depends on this capital N, right, which you should think of as thinking method. This capital N and same move there. Yeah, some type of connection, right? And okay. There's a substance of the following. So suppose P is an isotropic. Okay. You're thinking of this as, so the way I'm thinking of it is as somewhere over here. This adelic portion or X there. It's actually compact. Okay. So we just don't want to think about the cost. Okay. All right. So I'm assuming G is an isotropic, and then what? Then random test function. Okay. Yeah. Okay. The average over the ambient space with respect to invariant measure. Okay. On the orbit. It's an orbit, right? So we know what an invariant measure is. In fact, it's a finite module, I didn't say. This is true for any semisimple group. I'm trying to compare the measure on the average over the ambient space to the average over my wild orbit inside. Okay. About this in terms of what exactly? Complexity of the ambient space, I will say in a second what it is, over minimal complexity of my complicated orbit inside, or some exponent. E1 form of the function, that the function is power. Okay. So the theorem is basically quantitative. This is explicit in absolutely all of the objects that you could see. Okay. Let's maybe specify it. I will specify in a second what this means. The level of the function, right, is just basically the size of the compact open subgroup that my function is invariant under. It's a function on that space, right? And C1 norm is just I'm taking off an normal basis and see the algebra R. Okay, and just looking at derivatives. Those directions will look at. Consider how large they could be. Okay. Good. So yeah, the point in particular, right, is that this less here depends on nothing. Okay. Yeah. Not in particular, not on X, not on Y, not on the function, right? The complexity here, and you should think of it as something. For me, at least, I prefer the complexity for volume. But if you wanted to write volume, It's just some type of measuring how complicated the ambient object is. Okay, very explicitly, in fact, here you could take. You have the Lie algebra. You have to here, right? And I could think of the Lie algebra as being some rational subspace of the Lie algebra SLN. You can take the height of the rational subspace. That's what this is. Okay, it's perfectly good way of putting that. This minimal complexity here is basically what I was trying to explain before, not successfully, but the complexity of any intermediate object between y and x. Okay. So yeah, let me just try.
Depends on n, but not the embedding itself. The theorem depends on n, only depends on, but not.
Right. Okay. I mean, I'm hiding somewhere here, so something somewhere here, right? When I say that I measure the complexity, the embedding is encoded, right? Particular. Okay. Basically, I have some way, right, of embedding my Lie algebra. You get the Lie algebra of G into the algebra of SLN, right? And I'm measuring the height of the image, right? And there's no way of knowing what the height should be of the previous, of the Lie algebra of G itself. Right? So the embedding is encoded in this data. This minimal complexity, something that you can at least hope to calculate explicitly in all of the examples that you would give me. Okay. What is it? It's just let's have some more space. I'm taking the minimum, okay, of all of the objects that could sit between y and x, okay, much like on the torus that what we saw before. Okay, so I am taking a complexity of like this. It's where M here is just an intermediate group between H and G. Okay, in this sense.
So here again, I could take the Lie algebra of n and take its height inside.
Yes.
So then that
But is, oh, I'm sorry, I'm lying slightly. Of course, there is this shift here, right?
yeah, it's
Product law.
conjugated Lie algebra. Yeah.
Yes, exactly.
Yeah.
Okay. Of course, it's not by far not the first result in this direction. So maybe I'll explain what else exists. In particular, many things that we use here have already been addressed someplace else, right? It's important. Yeah, let me maybe discuss first results that exist over R, and then we can discuss results that exist over this. Okay, so over R, first theorem I'd like to mention this direction is what was the work of Einsiedler and Venkatesh. That's exactly in the setup that we had before, right? So when I mean over R, I mean G not gamma. Okay. G is in this case semisimple Lie group. In fact, gamma you would have to assume that it's commutative lattice. Yep. And so what they proved is quite striking. Is the case of orbits. Okay, of a single group H inside G. Okay, if H is finite centralizing. Okay. And finite centralizer it has loads of very nice consequences. Okay, it's For instance, assume that you had a centralizer. Okay, if I give you some orbit of H, right, a periodic orbit, what I can do very naively, right, is I can take that orbit and I can shift it around using the centralizer. Okay. That doesn't really work. Centralizer is fine, of course. Or maybe put differently, periodic orbits of H, okay? If the centralizer is infinite, they appear infinite, somewhat continuous families, and if the centralizer is finite, they in fact appear discretely, okay? It's a very important distinction. That one needs to work around, okay? And okay. Yeah, it's been a struggle for a while to somehow address this. There's special cases that remove the centralized assumption. Specifically, let me mention Amir Mohammadi. What they do, yeah, that's, you can think of, let me just write it very vaguely here. Thinking of SLN, okay, and I put inside SLN a group that is blocked there. Okay. Except for one case, basically, when this group here is SL2 and SL2, they show a similar theorem. Okay, maybe roughly of this type, not exactly. Yeah, because the group is fixed, but okay. And this, of course, has a centralizer, right? The centralizer here is the one dimension. Good. So that's that special case. Then there's Einsiedler and here. It's in spirit very related to what we're interested in here, actually. The view of the application is basically I want to consider SO1 sitting inside SON1. In which case, a centralizer is something like an SON -2, so in particular it's compact. Okay, that makes that's what drives essentially. Last thing is the direction that is worth mine. Well, only without centrals.
So your work was the general case without centralizing.
Yes, okay. There are some technical assumptions. Yeah. Yeah. Your work had this nice feature that you could say approximate some intermediate object polynomially in the volume. Can't quite do that because of intermediate things. But for equidistribution in the ambient space in this spirit, this is what I get. Okay, so that's work over R. Over the dells, there is a very nice work. In particular, very important for us in that context of Manfred Einsiedler. If H, or maybe out of H, that way I wrote it up there, in G is maximum. Okay. Maximal meaning how? Maximum meaning in the absolute sense. Okay. There's not only no intermediate group of a Q, but there's no intermediate group of the product. It's an important distinction. There is a nice work that doesn't quite fit in the setting. Where they look at basically, let me not write what it is exactly, but it's basically product case, okay, where you have some groups sitting inside a product and projections onto each of the factors will be maximal, but of course it's not maximal as a group, as a sort of product. Okay. Good. I have time to say something about it. That was also the goal. Okay, if there are no questions, let's talk about it. Space. I want to explain two things really. I want to explain how a theorem of this type, okay, can say anything in the direction of the application that we had at the very beginning, right, for global principles of quadratic. And just to be clear, that's not something that goes back to us. That's something that goes back to the theorem of Ellenberg and Venkatesh that we had earlier. Okay, but still, I think it's important to see. Kind of
Make sure I understand. So this term really tells you something, so to speak, for all G at once.
yes.
Okay.
Of course, I mean, yeah, things depend on height of G.
Right, but it controls that dependence completely.
Yes, in fact, I would argue it's quite crucial for us
Okay.
because proof is in some sense inductive.
Okay, I see.
And you,
Okay.
yeah. It's one of the things that makes the paper very lengthy.
Okay.
You need to keep track of all of the constants all of the time, right? To do this. Actually, I'll calculate it myself too. Okay. So, yeah, how does this theorem have anything to do with quadratic forms? Okay. So the relevant group here is mentioned it earlier, is the speaking group quadratic form. If you don't like it, take S O. At least for picture, it's completely sufficient. Okay. And so I'm thinking of the adelic quotient of this as of that. Okay. Now, in terms of what we discussed earlier, if the quadratic form Q, right, were indefinite, you can really think of this adelic space as an extension of a real homogeneous space. Something like this. I'm slightly lying when I write the C points, but okay. And that is if yeah, so if the quadratic form is indefinite, or put differently, if I had strong approximation. If I don't have strong approximation, what happens is that this group, that the adelic quotient doesn't sit above one such real homogeneous space, but in fact a finite collection of real homogeneous spaces. Okay? So let me get that. These spaces are parameterized by the genus of the quadratic form, or the spin genes in this case. Okay. So yeah, it's a finite collection. Okay. And so what happens is that by Hauser-Minkowski and some other analysis, but by Hauser-Minkowski, remember that we assumed that a quadratic form was represented by locally represented, right? By the quadratic form. Particularly, you could get a representation over the rational numbers if you wanted so, right? And that representation turns out to be actually a representation, not by our quadratic form, but by a friend of our quadratic form, named genus. It's a quadratic form that is equivalent to our quadratic form at all the places. Okay? And yeah, so what that does is actually, Minkowski would give you a representation, or maybe put differently, a very small orbit, okay, in one of those spaces. Okay, small meaning it's something like H or not H. H is compact, so it's not for us not very interesting. Okay. And H would be basically you find representation. You just think of subs so some type. If this were your representation, okay, H would be the group that fixes the group in the spin group that or SO if you wanted to that fixes this subspace pointwise. So it's basically all the which see if I can draw that. All the rotations. Okay. On the following complement of that direction. That's what H is. Right? But that's not a very interesting object. You have, on the other hand, above that object in here, I have something potentially very wild. Okay, it's the adelic homogeneous space. And if I'm lucky, okay, lucky meaning that I might apply this theorem, right? What would happen is that this orbit is so wild that maybe it sees a point that projects to this. Okay. Yeah. And in fact, okay, so this factor here corresponds to some open subset up here. Okay. And I can really think of this as some type of target-hitting problem. And if the order is sufficiently complicated, it will take this specific open set. So it's really that theorem for one function. Okay. That's how someone miraculously running out of powders. Okay. 5 points. I think above the portions I was reading, that would be exactly a representation by my quadratic. Okay. Of course, that's just a picture, but yeah. So there is quite a bit of thinking involved into seeing somehow that so this group H, right? We were saying it was a stabilizer of some subspace. Okay. There's a collection of obvious intermediate orbits, precisely stabilizers, let's say, of vectors in the subspace. Height of these stabilizers, okay, relates precisely to, of course, it's long gone, to the minimum of the quadratic form that we had written in the other field. Okay. And then there is an analysis involved to justify that this is the only thing we need to consider. Blah blah blah. Okay. So that's the doodle about going from this theorem to the other theorem. Okay. 5 more minutes, right? Use those 5 minutes to try to say something about them. Okay. So first thing I should argue is that there is some prime, okay, where the dynamics on this orbit, right, the complicated orbit is interesting. Okay, that's I raised it. It's written here before. That prime you can find using the subvolume formula. And that's what happened in that paper of Einsiedler, Mohammadi, and Venkatesh. Okay, and for us, so pick such a prime. Okay. And so consistently, which means that okay, it's a prime so that in particular it's a simple group here over QP has no complex factors. Okay, and I'm looking at the invariance group at that prime. Okay? Might not be exactly this group, but it's certainly a conjugate of that group. So yeah, that prime has many different properties that are important and letting that just to be clear. So I'm fixing some embedding at that prime because there's no compact vectors. I'm fixing some embedding of SL2 in the invariance group of Y. Okay. I'm going to call it H without the density equations. Okay. So what the proof does, okay, as in the previous works, is it tries to accumulate elements of the group that almost preserve my measure. Okay. And almost preserve just means that if you apply the element of the group to the measure, I can estimate the distance, let's say, on smooth functions, okay, between these two measures. Okay. How do I accumulate elements that almost preserve the measure? Here's a picture. So I have my space. Okay. And let's say the first step, I want to try to find one direction that almost preserves my measure. So I'm thinking of the orbit and sort of its sheets of this group H, right? And okay, let's try to draw that. Okay, so more sheets. Of course, we didn't quite succeed, but okay. And I know that the orbit itself is a large volume, so maybe I'll find points that have some distance and this displacement here is somewhat transverse. Okay? So the main dynamical input is what I have here. So let's say this distance is epsilon. Of course, the sheets have displacement that is somewhat related, to this complexity. And this epsilon here is at least, I need to take it to be at least the complexity of my orbit multiple somehow. Okay? And so the dynamics, I'm just zooming in on that picture, the points, okay? And I'm using dynamics, basically, I didn't write it, of course. I fixed myself some unipotent subgroup of this SL2. I'm using dynamics to shear these 2 points until they go to distance 1. Okay. Displacement that I found here, this displacement will almost preserve my measure. Of course, I am 100% lying here because who told me that the orbits would actually diverge, right? It could be that I was, so that's exactly it. So yeah, addressing the centralized discussion we had earlier, okay? Could be that 2 points that I found here, okay, don't diverge because the displacement might have been in the centralized. Nobody told me anything else, right? That's where we use some type of what is make divergence is a certain, okay? The effect of closing that one. Which we proved or recently with Lindenstrauss. What we did name show and the quadratic is quite similar. Okay, but so I'm just asserting that if for any typical points, right, in some sense, and yeah, you can exercise this displacement actually would actually go like this. Okay? And so what we end up with is some new displacement. Okay? And what I'd like to say is that okay, now give me this displacement. Just look at the group a new group. Okay, the group generated by my group and the new displacement. Yeah. And okay, it doesn't take very long to see that this is a horrible group. Okay. Because, well, potentially, right, it could be that, let's say, G here was very close to some other element where the group generated drops in dimension. It's entirely possible. Something similar could happen to H, okay? And so there is there's a big piece of somehow the work that I'm trying to emphasize that. A big piece of this work is finding a way to talk about these generation problems. Okay? To find basically a good perturbation of this that you found, so that it actually generate the reason. Okay, I'll stop here. Sorry for going over.
Questions? Could you say just briefly what ingredients go into this effective closing level?
Sure, it's a almost purely unipotent phenomenon. Okay. So what you should think of is let's say I take a unit. It has nothing to do with the specific setting here. All I want to say is that if I have a long unipotent orbit, and let's say for a lot of times, displacements where it would satisfy some weird condition, like in this case, right? They would almost normalize some specific directions as some specific Lie algebra that I know nothing about. Okay. One ingredient that I didn't talk about that goes into this habit was the inequality that needs to by the discussion we had earlier, right? It needs to make explicit how it depends on heights of the polynomials you're using, or etc. Yeah, that's what goes into this.
It's basically an argument. You sort of go and see which elements of gamma bring you back, and you take. So it's there's nothing sort of fancy. So.
But don't you have to check these elements are a lattice in that Zariski closure or something?
It's arithmetic setting, right? There is no Q, so you kill the kernel, the characters, and then Z points are lattice.
Okay.
You need to control the height of this group that you get after killing the kernel, but after that, it's not. Yeah.
There's another issue that, I mean, if you have toruses or something, their degree can be very large. It's sort of annoying. So you need to pass from, you don't look at the Zariski closure. You look at the smallest group generated by the importance over the complex numbers inside this.
Let's thank the speaker again.